Okay, so we'll start today's class, and in today's class we are going to continue what we discussed on Wednesday. In Wednesday, we have been talking about how we can make a computer network with some simple or small number of computers, and we introduced the idea of shared Ethernet. The idea of shared Ethernet was like if you have 4 or 5 computers, you can connect all the computers with a central device called hub, and the idea of having such a network is to realize centralized connection but distributed control, which means that all the PCs are responsible for the packets being sent and received. The hub is there only for transferring the information from one part of the network to the other part of the network. That means if PC1 is going to send something to PC4, then hub is going to take the packet from PC1 and it is going to replicate the packet to all the output ports except PC1. So it is the duty of PC2, PC3, and PC4 to either accept or reject the packet. Now, we have also discussed in our last class how the computers can do so. Well, in every packet, except apart from data, there should be some extra fields, and these fields should contain the address kind of thing. The addresses that we require for such kind of network is called Ethernet address. An Ethernet address is a physical address which is specific to a particular port. A computer can have multiple Ethernet addresses also, depending on if it can communicate in various different ways. Like it has an Wi-Fi port, it has an wireless LAN port, it has an Bluetooth port, and so on. Now, the construction and the operation of the network was discussed in our last class, and we have also identified the possible problems. The possible problems include the first one is the collision. Collision means there is a possibility that two computers are going to transmit at the same time, so there is a possibility of collision. Collision is not physically colliding of two objects. Rather, in this case, it will be a superposition of electrical signals. And when you impose two electrical signals on each other, then they will add with each other, and obviously the result is something different. So you cannot get back the original signals. So that's what we mean by collision. So collision is number one issue. The second issue is whenever you have more number of nodes, then the data rate that you get per user goes down. That is because it's a shared Ethernet, and at a time only one user pair can communicate via hub. So that's why if there are multiple user pairs, then they have to wait for their turn, which will ultimately reduce the overall capacity or overall data rate of the network. So that's issue number two. Issue number three is for not only large number of computers, but also if the physical distance between the computer and the hub increases, then also such kind of network is problematic because the length of the cable is a big issue. If the cable length is too large, then the signal will attenuate a lot and you cannot probably realize the transmission via those cables. So these networks are good for a start. These networks are good for a small office or probably 2-3 adjacent rooms. But when you think about bigger networks, this approach is not going to work, or this approach is not going to be scalable. That means you cannot simply have such kind of networks in every department, and then you can add all the networks or all the hubs with another hub. Generally, the idea of network is that we should have some kind of ignorance at every level. That means the whole network topology need not to be clear to every node, because it will be very difficult to keep track of it. Like when you are trying to communicate with something with another computer, if you know all the computers locations and their connections in the whole world, then it is bewildering and overwhelming information for your computer to tackle. So that's why when we make networks, we generally do in a hierarchical fashion. What we mean by hierarchical fashion, that means we connect some computers with a hub, and then in another building some other computers with another hub, and then we think of connecting those hubs. So in the second level of hierarchy, in the first level of hierarchy, we are just connecting the end nodes with the communication node, and in the second level of hierarchy, we are connecting these communication nodes or hubs with each other. Now we have two options for that. The first option is whatever we are dealing with, like we will have say 4 computers connected with hub 1, 4 computers in mechanical department connected with hub 2, 4 computers with in electrical department connected with hub 3, and then we connect this hub 1, hub 2, hub 3 again with another hub, which is probably in the computer center of our institute. So that is approach number 1. But this approach number 1 has the shortcomings which we have just described, that when the number of nodes increase, the collision increase, and so on. So in today's class, we are going to talk about like how with these small networks, a bigger network can be formed, but we are going to avoid some issues at least partially, which we seen in this particular design. So I'm going to today's slide. In today's slide, we are going to talk about this. This is called switched Ethernet. Now here, what we show is that suppose there are 3 such different Ethernets already made: Ethernet E1, Ethernet E2, and Ethernet E3. These Ethernet E1, E2, E3 are shown with dashed half circles. So every dashed half circle denotes a physically separate network. Maybe they are forming different branches of a department, or probably different departments altogether, and they have already got their own network. But now it is a task to connect these networks with each other so that we can have a communication between every possible computer in that network with others. Now in switched Ethernet, what we have done is we have got in the lowest hierarchy hubs. That means PC1 and PC2. If you see the diagram on the left side, PC1 and PC2, which are part of Ethernet E1, is connected via hub 1. Obviously, there might be more computers in Ethernet E1. I have not shown them. Then hub 2 is for Ethernet E2, which is connecting PC3. And on the right hand side, we are showing that hub 3, which are connecting PC4 and PC5. Now, in order to connect hub 1, hub 2, and hub 3, what we are doing is we are going to use a switch instead of a hub. We could have done it with a hub. The network would operate, but the network would have the issues which we described earlier. So with switch, we are not saying that switch is a magical device which will solve all the problems, but it will, to some extent, avoid the problems that we have described earlier. Now let's see how a switch works. And currently, all the hubs are being replaced with switches. And if you remember your old hostel days, in the corridor, when you see the flat metal box, rectangular metal box at the end, kept on probably eye level and connected via the Ethernet cables, and there were some green lights blinking. So those are switches I'm talking about, and these are the communication nodes I'm talking about. So how a switch operates? Well, again, we are not considering the whole world. That means we are not considering the internet yet, and we are just thinking that these computers need to connect to these among themselves. So there is no connection to the outer world yet. Then probably it is easier to understand. Once you understand that, then probably we can think of even more complex networks. Okay, so the switch is much like hub, but that means it is also having a centralized connection, but it is a bit more intelligent than hub. In case of a hub, if you remember our previous class, in case of a hub, the hub will simply copy all the packets to all possible output ports except the incoming port. However, in case of a switch, it does replicate the packets to the output ports, but it can do it in an intelligent fashion by looking at to which route it should replicate. Now, how it does such kind of thing? Well, the switch can read the addresses of the packets which we described in the earlier class. I hope you remember in our earlier class that we have introduced the concept of addresses. Addresses or Ethernet addresses are a field inside every packet, which are 48-bit long strings, and these 48-bit long strings denote a source computer and a destination computer. So in case of a transmission via a hub, the hub has no access to this address, or hub didn't try to read these addresses. However, in case of a switch, the switch is a bit capable, and the switch can read these addresses. And once it reads these addresses, it is capable of transferring the packets to the destination in a much more directed manner. So it's something like you had earlier an illiterate postman who is simply copying the letter and putting it to the letterbox to every home, assuming that whoever is the intended recipient probably will read the letter and others will discard. On the other hand, this time now we have a literate postman, and that literate postman can read the address on the envelope, and this postman can deliver the letter to the intended house only, or rather to the intended building only, and assume that the whole thing will be reaching ultimately. So if we continue our analogy with the postman, this network is something like you have got a letter and there is a literate postman, but the literate postman has no access to go inside the apartments. So he can read the address and can deliver the letter to the apartment, but inside apartment there is an illiterate postman who is probably copying the letter to every flat. So inside the apartment the inefficiency continues, but outside apartment at least there is an efficient mechanism. And it is also good that the letter is only contained within that apartment, because if you have an illiterate postman on the street, then your letter will end up in going to every house in the whole city. So we avoid that. So if you consider such kind of analogy, in this case we have a better idea with a switch. Somebody will ask, what happens if we replace all the hub with switches? Of course we can do that, then it will be much more intelligent. And actually the current networks are doing so. Earlier we didn't have this because the hubs were a bit cheaper and the switches were a bit costly. That's the only thing. So if we read the text, what it says is like it says that I'm just highlighting this part. So this highlighted part says whatever I have just described. It says that they can figure out the source, the contents of the data, and identify the destination as well. And because of the uniqueness, data goes to the relevant connection system only. So whatever I have just with an analogy with the postman and so on, that goes like this. Now let me talk about this figure a bit more. And in this figure, I will try to explain how an actual data packet travels from one PC to other PC, just like what I did with the shared Ethernet. Okay, so let's go back to the diagram. In the diagram, suppose PC1 wants to send some data packet to PC4. Now the data packet is having a form like two addresses and data. So that's what we are showing on the left hand side. I'll put my mouse pointer. So on this left hand side, PC1 is going to send some data, and the data packet looks something like this: S, D and data. So this is the data packet where we have some data part and we have some address part. In the address part we have two addresses, and it goes to this fashion. Well, PC1 has only one connection to the outer world, that is through hub 1. So obviously the PC1 goes to send the packet to hub 1. Now this hub 1 is a dumb device, so this hub will obviously send the packet back to PC2, but PC2 discards the packet. But the hub also sends the packet to this switch. Okay, so now this intelligence starts. In this switch, there is a table like this, which has two columns. One is the Ethernet address and the other one is port. So the switch knows, switch reads the destination addresses and forwards the packet to the corresponding port. That means the switch knows that if a packet comes with a destination address D, then D is connected to Ethernet port E3. So whenever a packet comes to a switch which is having a destination address D, it will only forward the packet to this port which is connected to E3, and it will not forward the packet to the port which is connected to Ethernet E2. So if we had used a hub here, then the hub would have sent the packet to the Ethernet E2 as well. But in this case, the switch can directly transfer the packet to E3 only. So obviously, the flooding of the packet in the whole network is reduced. Now, when the packet reaches Ethernet E3, it reaches hub 3, And obviously hub 3 again replicates the packet to PC5 and PC4, but PC4 accepts it and PC5 rejects it, and this is how the whole thing goes on. So obviously the difference here is made by the switch and the table it maintains. This table is a table between Ethernet address and port, and that's why the switched Ethernet is also called a layer 2 network. Now, what is a layer 2 network? Well, layer 1 network was the network that we described in the last class, where we had no intelligence. In layer 2 network, you can read the addresses and you can decide on the basis of the addresses. The layers actually refer here to OSI layers, which denotes different functionalities of a computer network divided into several layers. And higher the layer, more sophisticated the network is. We will be discussing OSI layers in our next class on Monday. So till that time, we will try to understand the layers as just an abstract idea of the functionality level or the sophistication level of a network. Okay, so this was the case for the switch, and then we can go further sophistication. Like now, we are not going to only consider the switched Ethernet. Rather, we are going to talk about the Ethernet with routers as well. Now, let us try to see what happens if we replace the switch with a router, the same network, and how the network operates with a router. And this is actually the highest possible sophistication possible for physical networks, because beyond router, all the functionalities are not taken care in hardware, they are taken care in software. Okay, so let's see the same network now again, but now with the help of a router. So you can see again we have three Ethernets: Ethernet E1, Ethernet E2, and Ethernet E3. They are shown with dashed lines. And the same PCs, PC1, PC2, PC3, PC4, and PC5 are there. Two PCs on Ethernet E1, one PC on Ethernet E2, and two PCs on Ethernet E3. However, the connection point, the central connection point, which was a switch in the earlier case, if you have forgotten, let us quickly go back. So here was a switch which was connecting these three Ethernets. Now we have a router. This router, this rectangular box is a router which is connecting the three networks. How these three networks are connected? Well, and how this whole thing operates. Let us try to understand the action of a router. Well, first of all, the router uses a different address pair. This address pair is called network address, or more popularly known as IP address. So the hub and switch, no, actually hub didn't read any addresses. The switch was working on the basis of Ethernet address, whereas the router is working on network address or IP address. The difference between Ethernet address and IP address is, I'm having the differences in this class only. I will be discussing in the next slide. But I'm just telling you that the major difference is Ethernet address is something like attached to hardware, so it is hardware address. On the other hand, network address is something like software-based address. So if a letter is coming to me via the Ethernet address, then I should be in my house because the Ethernet address is always attached to a place. So it is either my office or my house or something like that. So suppose I am buying something from Amazon, then Amazon is going to deliver it to a physical address. So unless I am in my office or in my house, whatever delivery address I have given, I am not going to get the packet. But network address is something like they can track me on the go. Like it doesn't matter to them whether I am in the office or in the home, they can still deliver the package to me because that address is probably my name or my identity, which probably is much more easily manageable. So let's see how this whole thing works. Well, the PC1 has two sets of addresses. One is the network address and the other one is the Ethernet address. So the PC1 has an Ethernet address of S and the network address of X. And it does not need to know the exact physical address of the destination computer. It only needs to know the network address of the computer. And knowing network address of a computer is much more easily accomplished because in dynamic allocation, these IP addresses are generated by the network itself. So it's not required before the start of a network to ping every computer and ask what is your address, something like that. That query is known as address resolution protocol anyway. But we don't need such kind of action which we require in case of hub or a switch, that before the network starts probably you have to ping everybody and knows everybody's address, and then only probably you can do. So in case of network-based address, the network itself assigns such network addresses. So it is good enough to know the network address of the destination. You need not to know the physical address of the destination. So what the PC1 does, the PC1 makes a packet like this, which has two sets of addresses. This is very important here. The router-based networks have two sets of addresses. One set of addresses is the XY, which is the network address, which is for the router, which is for higher layer functionality. The other set of address is switch or hubs, which are intermediate, which is having Ethernet addresses. So suppose we have shown here a hub, but there we can have a switch as well. So when the packet comes to this hub or a switch, suppose it's a switch, then it can read only the first pair of addresses, which is S, R1. See, here we have put the Ethernet address of S, and R1 is the port of the router that is connected to the network. So while making such kind of packets or data transfer, we only need to know our nearest router. We need not to know anything beyond the router. So that's how we design networks in today's world. Like when you are accessing your data from, suppose, Amazon or Google server in US, you are not directly communicating with that server. Rather, what you know or your computer knows is your nearest router. So you are going to gather the packets from your nearest router, and you are going to send it to the packets to your nearest router. And those routers will be deciding on which will be the next router and so on. So at every step, there is certain kind of, I should say, non-transparency or opaqueness, and this actually saves a lot of energy and calculations, because people need not to know about the whole network structure. Otherwise, it is very difficult for them to manage the whole thing, and it is very difficult to manage overall. So let us go back to the original problem. Like PC1 is going to send something to PC4. So it populates data in the packet. It populates the network addresses X and Y, but it also populates the Ethernet addresses, which are S, R1. So this address pair is needed for the journey of the packet between PC1 and router 1. So probably suppose here is a switch, and it can read that, okay, it is meant for R1. It can read the Ethernet address only. The switch, if it is a switch, the switch cannot read the Ethernet addresses. So the switch simply sends the data here. Now, when the packet reaches the router, it then reads the network addresses. So in the router, we have something called routing table. So what is a routing table? The routing table is much like the table that was maintained by a switch, but this time it is maintaining a table between network addresses and ports. So it now knows that, okay, suppose there is a packet which is having Y as the destination address, then it should reroute it through port R3. And it also reads the source address, and it knows the next time a packet is meant for X, that means the packet is moving in this way, the packet is coming from X, I should reroute it with R1. Well, at the beginning of the network, this routing table remains empty. And at the beginning, the hub, the switch, the router, everything behaves like a hub. But every time it sends a packet, it reads the data and it populates the routing table. It's something like if you go to a medicine shop, the medicine shop owner, before giving the medicine to you, he or she writes the name of the medicine in his order book, noting that okay, I'm able to sell this medicine, so probably I will need it later on. So it's something like that. It's a ledger book entry kind of thing. Every time a new packet comes, the router simply reads the source address, and it knows, okay, next time I need to send a packet to this guy, I know where to send it. So that kind of attitude the router maintains, and it populates the routing table. Obviously, the routing table has a fixed memory, so the old entries go trashed and the new entries come on top. So it's something like refreshed with every new packet coming through the router. Now, there is also and another table that is maintained by the router, which is called ARP table. ARP is address resolution protocol, which is a mapping between network address and Ethernet address. Why it requires? Well, when the packet finally leaves the router not only reads the network address, but it has to modify the Ethernet address part as well. You can see this packet is going here, this packet is coming out here. This portion X, Y, and data is same, but the first part, which is containing the Ethernet addresses, has been changed. How it is changed? Well, this router consults an ARP table where there's a mapping between network address and Ethernet address. So whenever it sees that the destination address is Y, it knows that the destination address should be D in the physical layer or Ethernet address layer, and it is coming out of R3 because R3 is connected to this, which is probably known from here. So from here it gets the information R3, here it gets the information D, and it populates the information R3, D here. So now onward, this packet will be tackled by hubs and switches, which will not access this network address part, which will only access the Ethernet address part, and it will deliver the packet on the basis of this information only, that there is a packet which is coming from R3 and which is intended for D. So you see, this hub or this switch doesn't know the original source of the packet. It appears for this switch that, okay, the packet is coming directly from the router. So such kind of ignorance is always maintained intentionally in case of a computer network, so that you only have the knowledge of the next hop. You don't have the knowledge of all the hops. So this is how the packet transfer occurs with for network with routers, and there are certain things that I want to talk about. First of all, I would like to talk about the OSI layers a little bit, because that will pave our way to our next class. In our next class, we will be talking about OSI layers. OSI layers are open system interconnection layers, and they actually define the level of functionalities. What I mean is, suppose there are only two computers which has a capability of communicating via hub. So that's a layer 1 network. Then switch, it's a layer 2 network. Then with router, then it's a layer 3 network. And this is how the sophistication increases. Now, the routers have also another interesting fact. The routers can be modified to have some kind of security as well. So you can have something like firewall, which can be installed in router. So as router is much more capable, obviously router is much more costly compared to a switch or something. Routers are capable, that means router has a lot of processing power and software, but still routers are not as big as a computer, but still they have more memory, more processing power, and more decision making power than the hub or switch. Now the routers can have some kind of firewall as well, and that will provide some kind of security. Okay, now let us talk a little bit about the IP address. In the last class, I have shown what IP address looks like. I have used an command ipconfig/all, and when you put ipconfig/all, then you can see all the IP addresses of the computer. Interestingly, the IP address of a computer are not limited by the number of ports. What I mean is, if a computer has only one capability communicating via, suppose, Wi-Fi, then it will have only one Ethernet address. But it can have multiple IP addresses tagged to the same Wi-Fi, because you can have several different services being run with the same Wi-Fi. Like you are probably downloading a file, you're probably doing some chat session, and you can have different internet protocols for IP addresses, internet protocol addresses or IP addresses for each of them. Now, an IP address is a 32-bit kind of address, and it is written in decimal. Interestingly, the Ethernet address is written in hex code. The IP address is written in decimal. I don't know why. Probably it was done for the first time in that way, and that exists till tomorrow. Like ultimately, everything is zeros and ones, but when they are shown, or when they are written, or when they are used, Ethernet address is always done in hex code. Possibly, hex codes are much more useful in assembly language, which is used for system software and so on. Whereas internet protocols are probably dealt with higher layer software people, who are more comfortable with such kind of a decimal kind of design. So they have something like 205.245.172.72 or something like that. So today I will just go once again with my computer. I will share my whole screen, and I can show you how the IP address looks like. So I hope now you can share the whole screen. And in the screen, I am going to type ipconfig/all. Then you will find not only Ethernet addresses but IP addresses as well. Let's go from here. So you can see that this IP address, I have a Wi-Fi IPv4 address, which is 192.168.1.203. Then we have this is actually connected right now, so nothing else is connected. So that's why we can see only one IP address. So I have an IPv4 address, and this is something like that. But there are certain things like so I'm stopping the share. Okay, so what I was talking about is there are more things like a subnet mask and all these things. We have some computer science people with us, so probably they know more about it. But those are the higher level functionalities, like how we can have a bigger network, how we can mask a part of a network, and we can have a subnet mask and so on. So that's beyond the discussion of today's class. Anyway, so I will go back to our original slides, and in the slides I was talking about routers and IP addresses. So IP addresses is a 32-bit software stored address, and they have this decimal kind of font, but every field has a range of 0 to 255. The idea of 0 to 255 is if you have 8-bit per field, then with 8-bit you can have 256 combinations, so you can denote numbers from 0 to 255. So there are 4 fields, A.B.C.D kind of notation, and for every field you have 8 bits, so you can have values from 0 to 255. Okay, and then there are some classes of network addresses like class A, class B, and class C, which you can realize with subnet mask, but again I am not going into those details. Okay, so we are almost on having less than 10 minutes, so we are going to talk about a little bit about MAC address and IP address. So the MAC address is the Ethernet address I was talking about, and IP address is the network address I was talking about. Now, they have certain distinctions between them. The MAC address is a layer 2 address, whereas the IP address is a layer 3 address. Now, this layer 3 address or IP address is a logical address. That means it is a software control address, and it will pertain to a single protocol. But layer 2 is a physical address, and it is connected to the hardware, which is the network interface card of the computer. And as I said that a computer can have any number of layer 3 addresses, but it will have only one address per LAN interface. So of course, if you have more LAN interface, then you have more than one Ethernet address, as I have shown, but per interface there is only one. Now the idea of 2 pair of addresses is described in this point. So what is shown here is that what I was talking about a few minutes earlier, that if suppose I have ordered Amazon something, so I need to always worry whether I have given my office address or home address, and I need to make sure that when the packet is delivered, I should be either at office or at home, which is sometimes a bit difficult. But suppose there is a mechanism that Amazon can deliver to me directly without bothering about whether I'm on office or in home, then it will be nice. So that's the difference between layer 2 and layer 3. So but if suppose such kind of possibility is not there, then there is only one option, that is to use ARP or address resolution protocol. Then there is another issue that is given in this point, that is suppose we are going to upgrade our computer. Now in that case, the new hardware comes with a new Ethernet address. So suppose there were already an existing network, and one computer out of 10 is being replaced. Now every computer in that network needs to know the new computer's Ethernet address, in order to communicate. However, in case of an IP address, even if you physically change the hardware, how frequent or doesn't matter, but still you can always communicate to the IP address because IP address is dynamic in nature. So it doesn't matter whether I push my laptop or my mobile or probably a PDA. Everybody can have a similar kind of IP address, which is probably easy to be conveyed to other computers. And finally, we have this address resolution protocol. The address resolution protocol is how we can map between the IP address and MAC address, how it is done. So before the IP packets are sent, we are going it through ARP. So how to so why ARP is required? Because we want the cache not to become too large. So the basic steps of ARP are something like this: that suppose there are two computers like PC1 and PC4, and they know each other's IP address, but they do not know the Ethernet address or physical address. So first of all, the computer who wants to know the Ethernet address of the other computer sends a broadcast kind of message. Broadcast messages are those messages which need to be delivered to every computer. There are certain such things. Broadcast messages are very useful while there is a collision. Anyway, so that packet is going to the internet recipient. The internet recipient says, yes, I am here and this is my Ethernet address. So this is how the list is populated, and this updates the entry in the list. However, after a certain time, the list gets refreshed again, and if the entries are very old, then it gets flushed out. So this is about ARP. So this is where we end today's discussion. Let me quickly go through a summary of what we discussed today from the beginning. Well, we have discussed a shared network in the last class where we can connect computers with a simple hub to form a simple network, and we have identified the construction, operation, and the issues with that network. In today's class, we have said that okay, if you are going to make network of networks, then it is not a good idea to use a hub to connect the networks. Rather, probably switch can do a better job. We have understood how a switched Ethernet works and how it can probably avoid some issues of the shared network. And then we have gone a bit further and we have shown how a network with a router can operate, and it can have much more flexibility and functionality over the switched Ethernet, which is a layer 3 network. So we have read about layer 2 and layer 3 network, but in the process, we have also understand that we need probably two sets of addresses. One is the Ethernet address, the other one is the network address, and we have understood what are the network addresses like, and we have also differentiated between Ethernet address and network address. And finally, we have read about ARP, which is a method of mapping between these two addresses. So here I end today's class, and in next class we are going to talk about OSI layers. So the next class will be the last class on the on computer networks. I know that these few classes are not enough to understand the big world of computer networks. That is generally a 2-semester postgraduate course, but at least you have some basic ideas of how computer networks work. And after Monday, we are going to start our new module, which is wireless communication networks, where we are going to talk about cellular phones, wireless, Wi-Fi, 1G, 2G, 3G, 4G, 5G, and so on. Okay, so I stop the recording now, and if you have any queries, you